Hello everyone, welcome to my channel. Remember to keep in touch, and the first set of videos that you're going to be seeing is this one, building a small language model from scratch. So what you're going to be seeing here is a series of lectures, and before I go into the list of it, reason why I've chosen this topic, right? Because I think since 2022 November, when I believe ChatGPT 2 was launched, um, large language models and generative AI is beyond fascination, has really changed the world forever, right? So I was truly intrigued and fascinated by what this large language model was, and clearly wanted to build one myself. And given the resources and the GPUs that are required, it is scale down the ambition, and now this is about building small language models from scratch, right? It's been since it was launched in GPT was launched to the public in November 2022. It's now been 3 years. I'm recording this in September 2025, and a lot of things have changed. So even the definition of get a view from Copilot on what is SLM, small language model, versus LLM. You can see the differences that it has, but it's always fascinated me was the language model parameter count, right? And you would see that SLM, when it started out in GPT-1, was about 117 million parameters, and today, when you talk about GPT-2, 1.5 billion, and then you can see really there's no comparison on the number of parameters, right? It's if you consider a large language model like GPT-3, it's been 175 billion parameters, and a massive scale difference, right? A small language model from scratch using PyTorch, and the model that we will be building is going to be about 30 million parameters. So it's somewhat comparable to interesting as we'll see how the response is. Now, for this lecture series, really it's going to be a 4-part series. This first one will be prerequisites and overview, where we'll go into the concepts of LLM, the architecture, and some of the key definitions. And then we'll go into the second part would be a code walk on how to build this LLM. And then we'll train and run this small language model, and then talk about fine tuning, right? So overall, the expectation from this is, and we would have the code which we would train on a large data set, and when we give a sentence like a LLM, this small LLM should predict the next token or the next word in the sentence that we provide, right? And we'll do that all from the grounds up. Now, before we jump as part of this prerequisites and overview, this lecture series is not going to be one where I am teaching you the basics, and it's not going to be that, because there are people who have created these tutorials and excellent study material, which is available free on YouTube, which I would strongly recommend here. In fact, all the things that I'm using is based on the learnings that I had going through the books and the YouTube videos that you have listed on this slide, right? The first one I would recommend is definitely the learning series from Dr. Rajat Dandekar from Visuara, and where he has really built an LLM from scratch, right? So Dr. Raj Dandekar has a series of lectures here. As you can see, I've gone through almost all of it. close to about 40 videos which in detail talk through every single element of building a large language model from theory with code and every detail on if you're new to large language models and want to learn about how that works. The second one is series is on, I won't say series. Really, the one lecture that I would strongly recommend is this back propagation from Andre Kapati. See here, it is actually the first part of the video of the lecture from Andre Kapati on on really he's building a micrograd engine, and he explains very beautifully how this back propagation works, right? Because as you all as you know, fundamentally LLM is a neural network, and we train this neural network by giving it a lot of sentences and content from the internet, right? So when as part of the training, you give a sentence, it provides the next token or the word, and you have the actual word that should be predicted, right? For example, Ravi likes to play, let's say, dash, right? And the LLM is trained to say it's badminton, and but the real answer is I like to play cricket. So it's going to take that difference, feed it back into the neural network where there are all these weights and parameters which will be adjusted based on the difference between what should have come and the one that is predicted by the neural network. So really this whole thing where you see how big the loss is and propagate it back. And this neural network is nothing but a set of partial differential equations that need to run back as part of back propagation, where you would tweak these biases and weights, which we call as the parameters, so that the right outcome would come, right? And of all the videos that I've seen, definitely the way Andre Kapati has explained it, even if you just go through the first half of this video for an hour, with the way he explains it in terms of how the gradient is calculated, how during back propagation these weights and biases, these numerical values are adjusted, I think it's simply get an in-depth understanding of how this works in large language models. The third one I would third one I would recommend if you are especially fond of reading books is building a large language model from scratch by Sebastian Rashka, and I think he is the person who and you can see it's on and I think even Dr. Raj had borrowed a lot of the explanations that Dr. Sebastian Rashka has provided, and this is this book, and definitely what this series is also based on is also the way he has put it in stages, right? The stage of building an LLM through the data preparation, the attention mechanism, and the getting the ILLM architecture first, and then pre-training the large language model, the foundation model, and then the stage 3 of fine-tuning. This is what we would follow as well in this lecture. All right. So now these are the so before to follow along this lecture, I would essentially say I request you to if there are learning gaps, or if you're new to LLM, to definitely go through Dr. Raj Dandekar's learning series, get your understanding of back propagation through Andre Kapati's lecture, and definitely if you love books, then Sebastian Rashka's build large language model from scratch, right? These are essentials. Now we are going to jump into this small language model architecture, right? What you see here is definitely something that you transformer architecture, right? So idea on, and that's where I got that diagram, this diagram as well, which is pretty much the standard that you see today in the large language model, right? The transformer architecture, and this was originally published in the 2017 paper from Google. It's called "Attention is All You Need" by this set of scientists from Google. And when it was first presented as this paper, and where they discussed this architecture, 2017, and then we see how it has evolved until November 2022, when ChatGPT 2 came out really for the whole world to see. It's been 5 years, and 2025, where we are, the amount of the way the field has transformed and is changing is really amazing, right? So coming back to the focus on this architecture, this is something that is I would like to walk through very quickly, right? So what you're looking at in this transformer architecture model is you get a, let's say you have a sentence or a text, right? And that sequence, right, is first encoded, right? And each of those words or tokens would be transformed into an embedding, right? And we'll talk about what is an embedding in this lecture series a little later. You can right now think of it as n dimensions, right? Like in the Attention is All You Need paper, each token, let's say the word V, would be embedded through a dimension of 512 values. You can think of that as a vector or a one row matrix of 512 values, right? And then that is added to a positional embedding, which says when you present a sentence, what is the position of the word in each of the sentences, each of the billions of trillions of sentences you're going to train this model on, right? So when that comes through, and then it goes through a certain normalization, and the multi-head self-attention, this is where the whole magic happens, right? Is probably the secret sauce. What essentially this does is self-attention, where when you present a batch of or a set of tokens, right? Tokens, you can roughly think of it as words. And what this does is it sees how these words are associated with each other, right? To understand the meaning, right? So essentially, when you're training a neural network with billions of tokens or words, yes, the position of the word is captured here. And really, multi-head attention, what does is it tells you what is the relationship between a set of words and how they are related to each other in a sentence, right? And the way that is done is these embeddings, as they come in, we multiply it by the transpose of that matrix, so to see how they are interrelated, and then that is what is queried and moves down the layers, right? And then there is a feed forward neural network, a typical network where you blow out the input dimensions and then converge back to the exact same dimensions. And this layer, you have several layers, up to 20, 50, 60 such layers, right? But essentially, for you to understand LLM, this is the core of large language models and the transformer architecture that's used by any LLM. Coding for in this series as well. And this is a diagram that I borrowed from Dr. Raj's lectures. And you can exactly capture, and this is what we'll be implementing, right? We're going to take the input. We're going to first, whatever is the text, we will tokenize them. So the words will be tokenized and assigned embeddings of a certain dimension, which is like a vector assigned to each token. Then we have the positional embedding, which is going to be the weights and parameters that will capture which word occurs at which point in the sentence. So the weights for that. And then what we just discussed here, right, the transformer block. So this transformer block will have a multi-head attention, and then the feed formal neural network. There is going to be some dropout, and of course layer normalization so mathematically we don't end up with calculations that don't converge. And once we have that flow, we're going to train this through millions of texts, and that's what will, once the language model is trained, we'll be using that to predict what should be the next word. Like, we're going to train it on about 2 million sentences, and then see when we provide a sentence what is going to be the next word, next word, next word, like that. So we can write out paragraphs and sentences, and we'll see if those come out to be meaningful. That's a quick overview of architecture, and what we'll head into now is really the key concepts, right? Like, we talked about embeddings, we talked about tokenization here. What do all these means, right? So these are some terminologies which we will go through step by step and understand one by one. The first key concept we want to discuss is byte pair encoding, which is really a very simple concept, right? So we all understand, if we are taking the English language, it's more than 400,000, 4 lakh words or 5 lakh words, right? So the computer is not going to understand words, it understands numbers. So we have to encode these words as numbers, right? So it's very simple. There are multiple ways to look at it. You can encode these words as within the 26 alphabet, maybe lowercase, uppercase, some special characters, right, in a small set of say 200 characters. That is one way of encoding it. Another way of encoding would be like having the whole dictionary of words, right? Like have those 400,000 or 4 lakh words or so in the English language. But you can intuitively see why that is not a good idea, because if you're going to one by one as an alphabet, or if you're going to have a large dictionary of words, you can intuitively see why that's not going to work, right? So for example, it's the variations in a word, right? Like hitting, he hit the ball, or boulder. So these kind of variations in the language is going to be hard if you're going to use just the dictionary of words. That brings us to byte pair encoding. Now, if you really understand byte pair encoding in detail, there is a video in the learning series by Dr. Raj, who would explain in detail what this byte pair encoding is. What I've done is really tried to leverage that learning, right? So there is implementations of this byte pair encoding. So what GPT or the GPT team have done is they have taken this concept of byte pair encoding. That is, they've taken a large body of text, looked at individual bytes, and then they club the bytes based on number of times it occurs. They've started encoding it, right? So what that essentially means is, instead of 4 lakh, the GPT-2 byte pair encoding, which is available in this tick token library, it's a range of numbers 0 to 5,257. 50,257. So we are really what we are looking at is in about 50,000 tokens, the words of English are covered. Now, rather than me talking, so this small program that I've written is going to essentially takes those integers and uses the tick token library, which is an implementation, which has the implementation of this GPT-2 encoding, providing it the integers and getting the decoded string. And it prints out pretty much all of it, right? And including the last end of text. And I also captured that in a spreadsheet format. So as you can see here, this byte pair encoding, initially it starts out with a lot of special characters, the numbers, and the alphabets, right? So if while this encoder, when it encounters words which it is not able to decipher, it just assigns them to the alphabets, right? And if you scroll further down, you would see some of the commonly occurring words and conjunctions and all those. It, is, an, or, and, ing. There is begin, there is beginning. So those are all showing up here. And then as you scroll down, um, some of these words, basically based on what it is trained, is captured in this list, right? So overall, for this large language model encoding piece that is converting the word to numbers, we are here is another example, right? I just took some token IDs for this string, right? Can I touch your wool? Woolly nodded his head and said, yes, Lily, right? So if I do if this is the text, and if I try to encode it, right, 1680. So in this, see that if I search by 1680, sorry, it's went to 11,000. Go back up. Is can, right? Similarly, the token ID 314 is I, and touch is 3638. So out here, this would be interesting, right? You would, it's actually a subword tokenization scheme, and the best way to express it is here, right? Like only, right? Wool, as you can see, is token 25749, right? And you would think that only is not one word. It's split as like this. It's split as 22173 and 5098. And what is 22173? If I look at my spreadsheet, that is the word WO, and that is a 5098 is actually only. So I need to probably go back up. Or not only, it's OLL, right? So this is subword tokenization, and the scheme is byte pair encoding, where instead of the whole word, it is split based on, so this word really is 2 tokens, right? So that is essentially byte pair encoding. The next key concept we'll go to is embeddings. We want to cover is embeddings, right? So again, this is a concept that can be easily understood through an example, right? So byte pair encoding, I've got this sample program. So we have understood the concept of a vocabulary, and we said for the LLM we went with this byte pair encoding and the GPT concept of about 50,257 tokens through byte pair encoding. So it's a similar concept here, where for embeddings we define a vocabulary, right? This would, think of it as these 50,257 words, right? And we are mapping that into we are encoding that into a number. Now, for each of these tokens, we are creating an embedding dimension, which is really in neural network is essentially weights that we are assigning to each of these tokens, and it kind of captures how each word is related to each token in the dictionary is related to each other. For example, king and queen would have a higher relationship, and like dog and cat would be related in certain ways, right? While dog and space shuttle might not be related. So this essentially, this neural network that we're building is going to capture the weights for the embeddings that when we say embeddings, it's referring to these weights, right? And uh, here we have a simple dictionary of 5 words, and we define their dimensions, embedding dimensions, to be 10, right? And what we are doing here is just looping through each of those uh, tokens and printing out the embedding and what embedding the neural network PyTorch a neural network library is able to provide. So essentially you get a value like hello is given these random values, world these random values, and PyTorch this one, and then embedding, so which is part of our dictionary. Now what happened, these are actually initialized values, that's all it is, right? And as we train the model, right, and when we back propagate and update these values, that's when the relationship between these words will, the ones which are related like king and queen, will have a higher value, while dog and space shuttle might have a much lower value, right? So that's how we essentially and all these will be tweaked, right? And typically this is just an example where we are saying embedding, it's a very small dictionary of tokens and then embedding of 10. Typically embedding dimensions are much larger. Even in our small language model, we're going to choose an embedding dimension of about 128, right? So that's so that that many dimensions are going to be there. I think in GPT-2 it was 568 dimensions, and then GPT-3 was probably 1024 dimensions. So each of those 50,000 tokens had a embedding dimension of 1024 or 568, and it's a huge number. So if I have to calculate, you're talking about 50,257, let's say, tokens, and if each of those tokens is going to have a dimension of even 568, say, you're talking about really uh, 28 million parameters, right, which captures the relationship between each of these tokens, right? So it's, you can think of that like a large matrix of these numbers of each of these tokens, and then when we back propagate, when we feed in a sentence, get an output value, see what is the output value, output token, and what should have been the real token, what should have been the output, we subtract and we back propagate. It's these, through partial differentiation is, and the gradient, that these numbers will get updated, and these weights will get updated accordingly to get the finally trained model on the embeddings. Okay, so this concept of embeddings is clear. Next we go into multi-head self-attention. This is like which is the core of the transformer block architecture. Now, to understand multi-head self-attention, um, the best way to explain, I'll try to explain it now, and then during the second part of the lecture where we are actually doing the code walk, I'll have a simple example so you can understand the mathematics part of it as well. Really, when I wanted to understand this multi-head attention, after doing the learning, I think this video from Welch Labs, where they were actually explaining how DeepSeek rewrote the transformer, there was first part of the video that explained this multi-head attention concept clear fashion, right? And I'll talk through this, right? We've covered so far this piece. Let's take, there is an example, the American flag is red, white, and blue. So that is the sentence that's come in. Now it would be tokenized, so it would have numeric values, and each of these tokens would have an embedding, and in this case the embedding dimension is 768, right? So when we are feeding this input in, this is a sequence of tokens with their embedding dimensions that is fed in into the transformer block, right? So when it comes into this transformer, relate to what we are speaking, we are talking through this, right? We are essentially talking about the tokens, their embeddings, positional embeddings coming into this transformer block, and we are talking about this multi-head attention. So what essentially happens there is we have three weight matrices, which are called the query, key, and value, right? Incidentally, they're also 768 by 768 parameters, right? So the query, key, value matrices. So again, just like you had the embedding weight matrix, this is also in a large language model trainable weights, right? So these are the weight matrices. So when we send this input in, what happens is the query, the weight matrix multiplies all three matrices, just multiply with the input, and we get the query, key, value matrices, right? Now, where the magic really happens is here, right? You have the query and the keys, right? And we multiply the query with the key transpose, which really captures, as you can see intuitively in a matrix, if you want to see how one element is associated with another element, you would do a transpose and multiply, right? That's essentially what happens here. So you would really be actually seeing if the American flag is red, white, and blue, then you are going to have, when you do this transpose and multiply, you're going to see how each of these words or tokens are related to each other. And that's what is the self-attention, right? You're seeing how these are related to each other, and accordingly those matrix values would go. If they are high related, they'll be having a higher value, and the ones which are lower will have lower or even a negative value, right? So that's what happens here, right? A query and key transpose, and whatever we get, it's called causal self-attention, because we are going to predict what is going to be the next word, right? So that's why you would see we would remove all those values which would be predictions, because those are not relevant. We're going to really train based on what the next token should be, right? And once you get this value, you can multiply it with the value matrix to get the, once we multiply that with we get the context vector and the output matrix, right? And this is a very good illustration of, as you can see, how the ones which are closely related have uh, higher values or color coded accordingly, right? So essentially this is the concept of multi-head attention. Why multi-head? Because this 768, we're going to split it into multiple heads, which is just the engineering piece of it, so we are not overloading and optimizing the memory and resources, right? So that's why it's called causal multi-head attention. Causal because we're going to leave out the output. We're going to use only the base of the matrix. We are going to predict the tokens that come out, and really the key thing is this transpose and multiplying with the query and key transpose, right, to see how each of these tokens are related to each other, right? um, so that's all there is. Once we get the context vector, then we get the that's the output matrix, weighted output matrix that comes out to go further through the transformer block. Now, going back, we've talked about multi-head self-attention. Next one is Softmax and layer normalization. We'll look at those concepts. Now, to understand the concept of Softmax, what I've done is Copilot and asked it the question, can you explain the concept of Softmax with an example for me, right? And what it's done is it's given the formula and how a Softmax is computed, right? And so what it ensures is all outputs are between 0 and 1, and sum of all outputs is 1, right? So if we have to, when we say we apply this query and key matrix multiplication, we apply the mask to remove the top portion of the matrix because we are going to predict the next token, and really don't need these values, and then apply a softmax on this. What we are doing is we are ensuring on these matrices that the value is all outputs are between 0 and 1, and sum of all the outputs is equal to 1. And essentially what they result in is a probability distribution of a value. So it tells you what is the probability of when the word the occurs, what is the probability of the word next to the being American or flag or that is captured here. Similarly, when the word American comes, what is the probability of these words occurring next to each other, right? So that's what the softmax does. And they've given an example as well with 3 words, and you can see how when we take these values and exponential and we do the exponent of that, like e is 2.72, and when we do the exponentiation of that, these are the values, they sum to 1122, and when you divide by that sum, it's these values. And that's what we are doing here, right? Like softmax is essentially that particular value divided by the sum of the exponents. So really what we see here is each of these values divided by the sum of the exponentials. It is gives a probability of their occurrence, right? So that's essentially what softmax is in a LLM. The next concept we want to understand is layer normalization, and you see that in the LLM or the small language model architecture as well. There is a lot of these layer normalizations happening, at least twice within the transformer block, and then once when it comes out, right? So you must be thinking, what is this layer normalization? I went to our friend Copilot to understand if it can give me and explain with an example how this layer normalization is used. And like a lot of times it's explained to me this concept very, very beautifully, right? And it says it's a technique used to stabilize and accelerate training, right? And what is more interesting is how intuitively you can understand it as you read further down, right? So if you have a set of input vector with a set of attributes, there is the mean and there is the standard deviation, right? More kind of like the average and how far the series deviates from the mean. And for each element, it is normalized based on that, right? How far away it is from that mean value, the average value, and also as a proportion of how much is the deviation itself, right? And the way it is useful in an LLM is once you compute this to normalize this, once you have this normalized value, right? Once the element is normalized, you typically have, for this layer normalization, you would have weights and biases, right? Like a very simple neural network, and the output would be these are the learnable parameters, or the parameters that would be trained based on what is the normalized element value, right? So these two would be updated during back propagation. They've also explained it very beautifully with an example. They've taken a simple vector with 3, 5, 7 as the value. The mean is 5. Standard deviation of this is 1.63. So when you normalize each of these elements, instead of 357 value, you're going to get minus 1.23, which is less than 5, and then 1.2347, which is more than 5 or the mean, right? And now if you assume that when you start training this neural network in this layer normalization, you're going to initialize those weights as 1 and bias as 0, your output would be the same, right? Like 1.230123. But this layer, now you can intuitively understand why this layer normalization very important before the large mathematical operations that you would do with multi-head attention, right? With query key value matrices, there's a lot of multiplication and a lot of processing going on. So layer normalization is really good there. And when it comes out, again, there's another layer normalization before going into the feed-forward network. So now I think we've covered a lot of good key concepts. Where are we? We are now after byte pair encoding, embeddings, multi-head attentions, and then softmax, layer normalization. Next, we need to understand this feed-forward neural networks, and you can see that it's a key component of this transformer block. Once it comes out of multi-head attention, we'll drop out some values, and then there is feed into, there's a layer normalization, and then there's a residual one where we just add the input here, and then goes into the feed-forward network. So what happens in the feed-forward network? Go to my trusted assistant, Mr. Copilot, to whom I asked what is the feed-forward neural network, and explained with an example. And once again, it explains how this is a crucial component that processes the output of attention mechanism and adds non-linearity and depth to the model, right? So it consists of a linear transformation, an activation function, and another linear transformation, right? So and they've explained it with an example. So essentially, when you're talking about some set of parameters, dimensions, it explodes those dimensions and then brings them back, right? So that's what the linear transformation is, which explodes that into a much larger linear transformation and then applies some activation function on it, and brings it down to the same dimension again, right? So that's what this feed-forward neural network is. You have given an example, right? If you have an input vector, this is for one token. If it has like 4 dimensions here, in the first linear layer, right, we would apply some weights and biases to transform that into a higher dimensional space. In this case, from 4, like this 1, 2, 3, 4, we are transforming that through the linear transformation layer into a higher dimensional space of 8 values. And then applying this activation function, in this case a simple ReLU function, which will, all negative values are zeroed out, and then bring it back to the original size through another linear transformation from 8 to 4, right? So that's all there is really to linear transformation. It's just a bunch of mathematical operations involving a linear transformation to a higher dimension, then applying an activation function, and then another linear transformation to bring it back to the original dimension it was. What I did was brought example, and this is an example of that, right? So I'm using PyTorch, and I took an input, right, which is really the first batch, right, with 2 tokens, which is the sequence length, and 3 dimensions, right? So here is the example. When I run it, you can see that it is the input is 2 tokens, and each token is having 3 dimensions, right? And now I'm initiating a linear projection layer, which is 3 by 9, right? Which means I am taking so this neural network, as you can think of it, it's going to have this neural network is going to have three inputs, and it's going to give out 9 outputs, right? So the weight matrix really is going to be 3 by 9, right? So for the linear transformation, when this input comes in, that is when this input comes in with 2 tokens and each token having 3 dimensions, when it flows through this linear transformation with of 3 by 9 weight matrix, then is going to just apply the transpose, right? Like 2 by 3 multiplied by 9 by 3 transpose, which will result in a 2 by 9 matrices. And since bias is true, it's going to add a bias as well, right? So that's what you see here. So this is the weight matrix, which is 3 by 9. And when we do a transpose of this and multiply for the linear projection, you are going to result, this is going to result in this tensor of size 2. So the 2 tokens are now in the 9-dimensional space instead of 3 dimensions space. Right? And it's pure matrix multiplication. And the output tensor is, we have also printed the output tensor here. So that's all there is to linear transformation, right? We're essentially taking it to a higher dimension and then bringing it back. You can think of once again, in any linear transformation, this is the weights which will continually during every training cycle, when we back propagate after one batch is done and update, these are the weights that are going to get updated, and that's how the large language model is going to get trained. So when we do this feed forward neural network, this is going to have weights and by we saw here in the example, and this weight is what is going to be trained. Of course, in a large language model, we are going to be talking about in our example about 384 dimensions, 568 dimensions, or 1024 dimensions is a very common one. And typically when this linear projection happens, into 4 is a common hyperparameter that is used when training LLMs, right? So if you are using, let's say, one token is 568 dimensions, into 4, this linear projection will take it to will have a 2272 by 2272 by 568 size matrix, which will get trained and as part of the LLM training. And eventually, when we complete training, these matrices will decide, these weights and parameters will decide what the next token should be. So that brings us to the end of this first lecture, the prerequisites and overview when building a small language model. That's the theory part. And just to recapture, we went through the learnings that you would really benefit from. And if there's a gap, you can go through these videos from Dr. Rajat, Andre Kapati, or Sebastian Rashka. We talked in detail about the small language model architecture, and then we discussed the key concepts of byte pair encoding, embeddings, multihead self-attention, softmax, layer normalization, feed-forward neural network. We touched on activation function a little bit as part of feed-forward neural network, where we just zeroed out some of the negative values. Variance scaling, we'll look at it during the code walkthrough itself. Right. So now that's a lot of theory that we went through. The next lecture series, we will jump right into the code walk, where we will build from scratch about a 30 million or 30 to 50 million parameter small language model, and then subsequently train it and then fine tune it and see how the result looks. So thank you. This was a long lecture series, but this was a long lecture. But I'm sure the code walk will be more fun.